Hello there, Physics 30. We are on to Chapter 14, Lesson 3. We're going to talk about the Compton effect and Compton scattering. Okay, these are the two things that we're going to kind of focus on. And these have to do with this experiment that Compton did where he shot X-rays at a thin piece of foil to kind of see what was going on. This is just for interest's sake. There's nothing really critical there. If you can click on this, see if it works. It'll be good on your Chromebooks, I think. All right, it's a good little kind of idea. So Compton effect is basically this concept right here. Okay, it's this concept here, where if you send an X-ray at a electron at rest, the electron will gain kinetic energy and momentum, but the X-ray will also change its wavelength. And so there's something going on where if an X-ray hits something, right, we have a loss of energy here, right? So this is an X-ray, it hits, and then all of a sudden its wavelength and its direction are changed, and that's a change in energy, okay? And so a change in energy, then we know work's being done, but we're also gaining kinetic energy on the electron, right? And since we're gaining kinetic energy on the electron, the energy here has to be lost, which means that this originally had to have some kind of kinetic energy, right? And so this is the big thing, right? Is that the photoelectric effect demonstrated that photons have kinetic energy, even though they do not have mass, and the Compton effect demonstrated they had momentum as well. So the photoelectric effect told us we have energy, right? That's the last lesson, right? Where I can shoot a photon that causes the electron to leave its orbital, right? And that's because it's gaining energy, right? And then it also said that they have mass, and this is the Compton effect, or have not mass, they have momentum, right? They don't have mass, but they have momentum, right? So that's an important little thing here. Okay. So what Compton noticed is what he did this. Okay, he could kind of predict it. All right, and the way he did is he basically said, okay, the wavelength, the change in wavelength is equal to h over mc 1 minus cos theta. What you'll notice is that h is a constant. M is the mass of an electron, so it's also going to be a constant, and c, the speed of light, is a constant. So this whole little packet right here, that's all a constant. All right, and then of course we have the change in wavelength and 1 minus cos theta. Make sure you do the 1 minus cos theta before you multiply by the h over mc. Okay. All right, so the maximum change in lambda is 0, right? So if the wavelength's coming in this way, right, 180 means it would be going backwards 180. The minimum is that if it's going in like this and then it keeps going this way, it would be a change of 0. All right, so we can't have an angle of 220 or anything like that, okay? So we don't have to worry about measuring from a certain angle. This isn't your formula sheet. Again, if you have the old new one, it'll kind of be in this area, but it's right here under quantum mechanics and nuclear physics. Right, this is our Compton scattering equation. All right, so it's right there. All right, don't worry about this. If you can click on it, that's great, but if not, don't worry about it. That's just an applet. So from here, Compton kind of knew the wavelength of electron. Okay, and what that means is that it kind of changes our understanding. Is now we're looking at an electron as possibly a wave as well, not just light, right? And so that's a big idea. So the maximum change in a photon wave occurs when it scatters backwards, and the Compton effect is really only important for gamma rays and X-rays. As anything larger, the change in wavelength is really not noticeable. So an X-ray photon of wavelength 0.0500 nanometers hits an electron and scatters an angle 30 degrees. Calculate the wavelength of the scattered photon. So we're going to start that equation. Right. Oh, probably need to actually draw it. Don't need to just do that. You guys can't imagine it. So delta lambda equals h over mc 1 minus cos theta. Right. Whenever you're doing delta lambda, it's always final minus initial, right? So my final is what I'm looking for. My initial is 0.05 times 10 to the negative 9. H is Planck's constant, which is in joules. So this is the 6.63 times 10 to the negative 34. My m is the mass of the electron, which is 9.11 times 10 to the negative 31. And that's multiplied by the speed of light, which is 3 times 10 to the 8. That's going to be 1 minus cos, and our scattering angle is 30. All right, so we're going to do some math. We're going to kind of work our way around to this, right? So we'll start by doing 1 minus cos 30. Okay, and then I'm going to multiply that by this 6.63 to the negative 34. Then divide by 9.11 to the negative 31. Then divide by 3 to the 8. Okay. And then you're going to add 0.05 to the negative 9. And what you're going to get is 5.03 times 10 to the negative 11. So what you're going to get here is to negative 11. So we got a very small scattering, okay? All right, so that kind of makes sense. All right, and that's just putting in the numbers the way they're supposed to be in. I'm just going to double check that, as you should whenever you're watching my videos. Yep, 5.03 times 10 to the negative 11. Okay, so that's that answer, and that's in meters, right? We could also do this in comparison of the way it was given to us. 0.0503 times 10, oh, not times 10, just converted that to nanometers, right? So we got a scattering, but not much, right? Very small scattering. All right, so in the Compton effect experiment, the following data was also collected. So we can also do it this way. We're given this, so same idea. We're going to start with that first equation, right? Instant and scattered. Scattered is the final, right? So this is the final. This is the initial. All right, and this is going to be H over MC 1 minus cos theta, not eta, theta. Jeez, brain's got to fire up this morning. Cos theta. And so the difference between those is 5 to the negative 11 minus, 5.12 to the negative 11 minus 5 to the negative 11, which is 1.2 to the negative 12. So 1.2 times 10 to the negative 12. All right. This part right here, the H over MC, this is the same as last time, right? So it's the 0.63 times 10 to the negative 34 over 9.11 times 10 to the negative 31 times 3, 10 to the 8, 1 minus cos theta. Okay, so what we're going to do here is we're going to just make sure that we take this whole thing right here, simplify it, and this number gets divided by whatever this is, right? So make sure when you're dividing this, you guys, that you have the denominator all in brackets, or divide twice, whichever works better for you. Okay, now you should get 2.42 times 10 to the negative 12. All right, so 1.2 times 10 to the negative 12 equals 2.42 times 10 to the negative 12, right? It keeps going. I just put 2.42. It's 2.4259, right? Minus cos theta. So then take your 1.2 to the negative 12 and divide it by the answer, or divide by what number you got, this number here, and you're going to get 0.4946606. Okay, 335 equals 1 minus cos theta. I can switch the cos and stuff over, so cos, ran out of space here, sorry. I'll figure it out. So then cos theta equals 1 minus that number, which is 0.505. Okay, that's just an algebra thing where I moved the cos. The cos went over to this side by adding cos, and then I subtracted this number over to this side, so it's 1 minus that number. Okay, which we then do the inverse cos of that, and we're going to get 60 degrees is our final answer. So sorry about that, you guys probably couldn't see that very good at the end. All right, so that's how we solve that, is we work it backwards, okay? Yeah, it's a lot of large numbers and stuff like that, so try not to make little mistakes here and there. Okay, so this is the theoretical important part, is that in momentum we learned that if something started with zero momentum, it had to stay with zero momentum, right? So there's this electron just sitting there with zero momentum, right? And I've got a wavelength that's going to come and hit it. After the wavelength hits it, I've got momentum, right? P does not equal zero. All right, we know that's impossible unless there was momentum initially. So what that tells us is that there has to be some momentum here, some momentum. But again, the issue with our waves, our photons, right? What's the issue with them? Well, they're massless. They're massless. So since they have no mass, how can they have momentum? This is where we're going to bring in a few things, all right? So first of all, since a photon has no mass, we can't use m. But what we can do is we can look at two equations that make sense. So first, the equation we can look at is P equals mv. We know it has momentum. Momentum's in terms of mass and velocity. Okay, we know that. Then we also know from Einstein's energy equation that E equals mc squared. So if we isolate m on both of those, then we can say m equals m. M equals m. Then we bring these in, right? And we get this E over c squared equals P over V. So we can rearrange and we get two kind of equations out of this, right? And so we get this first equation here, which is on our formula sheet, which is E equals the momentum times the speed of light, okay, right? And notice that this comes from the concept that V would end up being C, right? And so that kind of makes sense, right? And then we can also break this down into more things. So this equals PC, okay, energy in joules, momentum in joules seconds per meter, or Newton seconds, and the speed of light is 3 times 10 to the 8. And that equation is right here on our formula sheet. It's right there. All right, also under quantum mechanics and nuclear physics. All right. But from this equation, right, we can break this down more. We get a whole bunch more stuff. So this is not on the formula sheet. This one is, right? The more we break these down, the more we're connecting. So we're really connecting these equations a lot. So it seems like atomic physics and nuclear physics have very few equations, but there's a lot of information packed into them, and they all kind of link together. Since they all kind of link together, then we have to find these pathways where we're using 2 or 3 or 4 equations. Right, so this one is on your formula sheet, right? That's a very common one, so they use it on a formula sheet. Okay, and we can go from there. All right, so it's right here on our formula sheet, right? P equals h over lambda, h being Planck's constant, lambda being the wavelength. All right, so if you look here, we've got for anything with mass, this is the units we use, kilograms per meter per second. But if it doesn't have mass, it's joules per second over mass, or meters, okay, joules per second over meter, joule seconds over meter, or newtons per second, Newton seconds, right? So there's all those different versions of the answer. Okay, so which of the following photons have a greater momentum? One with a wavelength of 500 nanometers or one with a wavelength of 2 nanometers? Explain your reasoning. Well, if we think about it, the equation we're going to use is that P equals h over the wavelength, right? So if I think about that, if the wavelength's on the bottom, the greater the wavelength, the less momentum, right? So therefore, the 2 nanometers should have a higher momentum, right? And so if we think about that, we just do the 2 nanometers over here and 500 nanometers over here, right? So in this case, P equals over 2 times 10 to the negative 9. And you get 3.315 times 10 to the negative 25, right? Do it in seconds, why not? Can use that. And this one here, do the same thing. Nine. And you're going to get 1.326 times 10 to the negative 27. Okay. So when you're comparing those numbers, these numbers, the numbers out front don't actually really mean much, right? They don't really mean much. Like 3 times 3.13, yeah, 3 technically is higher, but what makes this number higher is that's only to the negative 25 versus this is negative 27, right? So therefore, the lower the wavelength, right, the shorter the wavelength, the higher the momentum, right? Which means that our gamma rays have the most momentum, etc. All right, so good luck with this. Okay, practice problems 28 through 33, then read questions 12, 13 to 16, then today's guide, and do 14.4, 14.5. Alrighty, have a good one.